Today we're going to talk about ionic bonds. Now, ionic bonds, as the name suggests, occur between ions. Specifically, they occur between ions of opposite charge. One of the components will always be a cation, and another will always be an anion. So today we're going to look at how those bonds occur, thinking about the transfer of electrons. Okay? Now, not all bonds that are ionic are formed in this way. Often ionic bonds are the result of two particles or more that are already ions, right? That are already positive and negatively charged and don't start off as elements. But today we're going to look at a situation where if two particles start off as elements, as atoms, right, in their atom form, and become ions, we're going to look at how an ionic bond is formed that way. So the example that we're going to use is sodium and chlorine. Okay, sodium and chlorine. Now sodium is Na is our chemical symbol, so we're going to draw that in this space. Right, because what we're drawing right now is before any transfer of electrons has occurred. Right, we're going to draw these two things first in their atom state, meaning that their protons and electrons are equal. Now sodium, if we look on the periodic table of elements, right, it is right here, and we see that it is in the first column. Now we're going to draw its Lewis dot diagram, right? So that's the diagram where we have the chemical symbol, and we have dots that represent our valence electrons. Now if we look here, right, sodium is element number 11. That means that it has 11 protons and 11 electrons in its atom state. It is also in the third row and in the very first column. So this tells us that sodium has 3 energy levels, so it's in the third row, and it has just one valence electron, right, because it is in our first column. And our valence electrons, remember, are determined by the number of electrons in s orbitals and p orbitals. Now this periodic table is color-coded based on where the last electron falls. Is it an s orbital, a p orbital, a d orbital, or an f orbital down here at the bottom in blue? So sodium just has one valence electron. So in our Lewis dot diagrams, that means we draw just one dot. Now, to help us see this a little bit better and to help us tell the difference between our cation and our anion, I'm going to color code this in orange. Doesn't look super orange against the blue, but it is orange. Orange. Now, in our sodium atom, right, we have 11 protons. Remember that those are positively charged. And we have an equal number of electrons, right? That's what makes it an atom, right? And those are negatively charged. If we have equal numbers of positive and negative charges, right, that means that our net charge, our total charge, is 0. Now you might be asking, why is there a line through that 0? There's a line through that 0 because in chemistry we have to write a capital O by itself a lot. So if I wanted to say I have 0 oxygens, it kind of looks like I'm about to make googly eyes, right? And so instead, I always draw a line through my zeros so that we can see more clearly that this is 0 oxygen, although this kind of makes me want to make it have like an eye patch or something. So I always draw a line through my zeros when I have a 0 by itself so that I can more clearly distinguish that I mean a 0 rather than a capital O. Now sodium, if we look at an electronegativity table, we'd find that sodium has an electronegativity of 0.9. This, of course, is a lower electronegativity, so that means that it's clearly a metal. That also means that it doesn't do a really good job of hanging on to its electrons. So this little electron, right, is easily given away by sodium either to form a metallic bond or to form an ion, right? So this electron is going to go away, right? That's what's going to happen to the valence electron on sodium. So we can say that sodium will lose its valence electron. All right, so now let's go and take a look at chlorine. Now, chlorine is a nonmetal. and it means that that is on the right side of the periodic table. So I'm going to draw our chlorine here in green. Here's our chlorine. And if we look at the periodic table, right, we can determine how many valence electrons it has. Now if we look here, our chlorine is right here on the periodic table. And remember, only s and p orbital electrons count towards our valence electrons. So that means that we can just count from left to right to figure out how many we have. So sodium has 1, right? So that means magnesium has 2 valence electrons, aluminum has 3, silicon has 4, phosphorus right here has 5, sulfur has 6, and chlorine has 7. So that means I need 7 dots around my chlorine. Remember, the order that we learned to add the dots was top, bottom, left, right. But now that we're a little bit better at it, hopefully, you can know now that technically you can start on any side. And as long as each side has 1 electron before you double up, you can technically add them in any order. And that is because these are 3-dimensional structures. And they're not actually, these electrons are not actually in squares. They are actually heading out in 3-dimensional space. So we can also think about it, right, as if our chlorine is in the middle, right? We are thinking we have electrons going up. We have electrons coming toward us, right? Coming toward us, and we have electrons kind of in that same plane. And we actually have electrons going away from us too, right? So this is actually extending in 3 dimensions. So if you turn it different directions, right, you're going to end up with a different layout. All right, so chlorine here, actually, if you look at the periodic table, has 17 protons. Remember, protons positive, electrons negative. And it's because it's an atom, if we have 17 protons, that also means that we have 17 electrons. Because we have equal numbers of positive and negative charges, that means the net charge of this substance is 0. Now, if we check an electronegativity table, we would see that the electronegativity of chlorine is actually 3.0. That is a pretty high electronegativity. Remember, the max electronegativity is 4. So 3 is pretty close. So that means that it's really good at hanging on to electrons. So good that it might actually attract electrons from other atoms. So what will happen to the valence electrons on chlorine? Chlorine will gain more. Will gain an additional valence electron. All right, so that's what these two substances look like before anything happens, right? We have this sodium, we have this chlorine, they are both atoms, they both are unhappy, right? Neither of these substances exist as single atoms in nature. Chlorine as an element actually is found bonded covalently to another chlorine, and sodium is found bonded to other nitrogens. Sodium is found bonded to other sodiums. Different element there. Sodium is found bonded to other sodiums through metallic bonds, right? And it's bonded to a whole bunch of them through metallic bonds. Chlorine is found just as something I call a diatomic molecule. So di meaning 2, atomic meaning atom, molecule meaning molecule, right? So these aren't actually found all by themselves in nature. So clearly something has to happen for them to be a little bit more stable. So what actually happens is they become ions, right? And when they're in their ion form, they can bond. All right, so we're going to draw them over here after the transfer of electrons has occurred that results in our chemical bond, right? Because they'll be electrostatically attracted to each other due to their opposite charges. So we're going to again draw our Lewis structures. Now, in this case, we are not drawing an atom anymore. We are drawing an ion. And that means that 1, they're charged, and 2, that's going to change their electron distribution. So we know from previously that sodium will lose its valence electron, right? So that means that we are not drawing any dots on sodium because it lost it. It's gone. That also means now that we have still 11 protons, but we lost 1 electron. So instead of having 11 electrons, we now have 10 electrons. Now, if we look here, right, remember that charge we can determine by taking protons minus electrons, right? And so this gives us a +1 charge, right? Because we have 1 more proton than we have electron, which of course makes this a cation. Now this, we're going to add to our diagram here a plus sign, right? Because we need to indicate that this is a positive charge. Now let's turn to our chlorine. Our chlorine is still going to have 17 protons, but now instead of 17 electrons, it has gained an additional electron, right? So we can see here that it has one empty space that can be filled up, and it wants to fill that space up. So it wants to have 8 in its outermost shell, its valence shell. So we're going to now have, instead of 17 electrons, we are going to gain 1 to get 18. Now, remember, electrons are negatively charged, protons are positively charged. If we have more negatives than positives, then we're going to have a negative charge. Now, I know, thinking about adding something and it becoming negative is super tricky to remember and think through. Remember, we are adding a negative charge. You're adding a negative. That is the same thing as subtracting, right? So we are going to have a negative charge, and it's going to be a -1 charge, right? Because we have 1 more electron than proton. Because it is a negative ion, we call this an anion. Y'all, this is why we did a whole unit on ions before this, so that this would not be new information, right? So let's go ahead and add in our electrons on chlorine and go ahead and add the charge to our diagram. So just like last time, right, we have the 7 valence electrons. Right, these are the ones that chlorine started with. I'm drawing these in green so we can clearly see this. And we have an additional electron, right, because chlorine gained 1 more. Now, in this case, where did it get that electron from? Hopefully you're thinking, sodium, it came from sodium, right? So we're going to go ahead and draw that in orange, right? Because that electron had to go somewhere. It couldn't just disappear into nothingness. It had to go somewhere. And so we're going to add it to our chlorine right here. This also means that our chlorine gets a negative charge, so we're going to add that in there. Now, what happened to the electrons in this process, right? This right here, now these two will move closer together and they will be ionically bonded, right? Because they are opposite charges, which therefore attract. So what happened to the electrons? The metal lost an electron to become positively charged. The electron was gained by the nonmetal to become negatively charged. Ooh, really getting out of the box here. Right? Become negatively charged. So we can see how we added that electron, moved to chlorine, right? And now we have 2 oppositely charged ions that create an ionic bond. Now let's go ahead and take a look at the rest of this page before we wrap it up. So looking at the rest of this page, there's mostly just a guide, and this is going to be really helpful for you when you get stuck on thinking, crap, how many valence electrons does this have? What happens first? When we're thinking about this electron transfer process, you always want to remove electrons from the metal first, right? Because you can't just create electrons out of nothing, right? They have to come from somewhere. And so they always come off of the cation. That is the supplier of our electrons, right? And then they move over to the anion. The anion always forms second. Your cations are going to be metals, with a very rare exception, right? Hydrogen is basically the only exception to that, and it can become a cation, but all the rest of them just about are going to be metals. You can usually assume that a cation is going to be a metal, which means that our anions are non-metals, and that is almost more universally true. It is very, very rare for a metal to form an anion, so rare that we ignore it. Usually it's only under more extreme circumstances. And this is because, right, metals form cations because they have these low electronegativities. They're really bad at attracting electrons. They also have low ionization energies, meaning it doesn't take a lot of energy for them to become an ion. So it's really easy to pull an electron off. They don't hold on to it well, which means it doesn't take up a lot of energy. This also means that they drop down to a full octet, right? And what we mean by that is if we look at a Bohr model of a metal, for example, sodium, right? So if we look at a Bohr model of sodium, right, we can see when sodium becomes an ion, it loses its valence electron. So this electron goes away, right? And so when that disappears, we have a new outermost energy level. And let's take a look. Let's see if we have a full octet here. Right, remember, an octet is 8. We have 1, 2, 3, 4, 5, 6, 7, 8. Right? So this right here is a full octet. So our metals drop down. They lose their valence shell entirely to become an ion. Right? They lose their electrons and become positive. Now, in our anions, they're really good at attracting electrons, and they have really high ionization energies, which means you cannot pull an electron easily off of a nonmetal. It takes a lot of energy, and so they attract electrons. They will take in electrons, and they fill up to a full octet, right? They'll gain more in order to do that full octet, like we saw with our chlorine up here. Right? They gain electrons to become negative. I know, gaining and becoming negative, like that doesn't, it takes a minute to process that. If you remember that electrons are negative, then it makes it easier to think about. All right, so we're just going to fill in this key down at the bottom real quick. And this is just going to help us just as a kind of a cheat sheet, okay? So anything with one valence electron, it forms a +1 ion, okay? And some things that are going to do that are hydrogen, lithium, sodium, and potassium. Now, I just wrote our chemical symbols here because it's way faster. So anything with one valence electron forms a +1 ion, and that's H, Li, Na, and K. Hydrogen, lithium, sodium, and potassium. All right, two valence electrons things, they form a +2 ion. So the most common things here are beryllium, magnesium, and calcium, right? So things with a 2 valence electrons form a +2 ion, right? They will lose both of their valence electrons. And the elements are Be, Mg, and Ca. Beryllium, magnesium, and calcium. Let's zoom in a little bit more so you can see this a little bit better. So lastly, we have 3 valence electrons. So anything with 3 valence electrons, you maybe are getting the pattern, form a +3 ion. And so those things are largely going to be things like aluminum and gallium are going to be your most common ones. We sometimes include boron in there as well, but it's mostly going to be your aluminum and gallium. So remember, these things, right, these all form cations. They form positive ions by losing all of their valence electrons. We're going to move over to our anions now, and these, remember, they gain electrons to become negative. They gain electrons to get a full octet, right? So we got to think about how many electrons do these number of valence electrons need to get to 8, right? So things with 7 valence electrons, those are all of your halogens, fluorine, bromine, iodine. These form a -1 ion. Okay, so again, these are our halogens: fluorine, chlorine, bromine, iodine. So anything with 7 valence electrons forms a -1 ion. They gain 1 additional electron to get that full octet. And again, these are F, Cl, Br, and I, otherwise known as fluorine, chlorine, bromine, and iodine. Next, we have 6 valence electrons. Hopefully you're seeing a little bit of a pattern here, right? We had 1. What's going to be next? 2. Right? So things with 6 valence electrons form a -2 ion. And these are going to be, largely it's going to be oxygen and sulfur and selenium. Okay, so things with 6 valence electrons, anything in that column that is a non-metal, right, is going to form a -2 ion. So that is O, S, and Se, oxygen, sulfur, and selenium. It's been a long day, y'all. All right. So last but not least is things with 5 valence electrons. So just like things with 3 valence electrons formed a +3, because they lost 3 electrons, things with the 5 valence electrons gain 3 electrons, right, to get to 8, and so form a -3 ion. And so these are going to be like nitrogen and phosphorus. So N and P. These both form a -3 ion. And if you actually look at their Lewis dot structure, that kind of makes sense, right? If you look at it, you'll see that there are 3 great spaces to make a bond, or to gain an additional electron, so that it can become that ion. All right, y'all, so this is where we're going to end for this video. Tune in for another one. You can leave this up so you can make sure you have everything written down.